Okay, so good afternoon, good night, good morning, all around the world. I wanted to be a bit more explicit with an example about the proof by induction, which I did last time. And, any problems? Can you please switch off your mic? Okay. So, for example, this is a simple graph, and this is its adjacency matrix. You can, let's assume that we are at a level h equal 3, meaning that we want to compute the number of 3 walks from one vertex, from each vertex to any other vertex, okay? So first, the inductive premise was what's the number of one walks from one vertex to another. That's clearly directly the adjacency matrix. Why? Because a one walk is just going through one edge. And going through one edge is exactly what is described by the adjacency matrix. Okay? Next, assuming that we have proved that a raised to power h minus 1 is exactly the matrix whose entries represent the number from one vertex to another. It is so, but this is not the important thing. Assume it is, and actually it is, okay? You can check that, but it's not important in this moment. I want to show you how the inductive step works, okay? So, for instance, let's say that we want to find the number of 3 walks from, say, V1 to V5, okay? And so this means that we have to take all 2 walks from V1 to other vertices and then a last edge towards V5, okay? Let's look, so V1, let me see whether we don't have any, okay, I'll just underline. The row corresponding to V1 in A square is this, and the column corresponding to V5 in A is this, okay? So now, if we want to see how many 3 walks there are from V1 to V5, we do this. We take out the last edge, so to say. And so, if I want to see a 3 walk from V1 to V5, I'll have that the last edge of that 3 walk is either this or this, okay? And up to here or to here, I must have a 2 walk, okay? And so, let's see, from V1 to V2, from V1 to V1 itself, I have 3 2 walks. Don't you believe that? Can you see them? They are simply these 3 walks. 1, 2, 3. 1, 2, 3. 1, 2, 3 is, sorry, 2 walks. So 1, 2 coming back from V1 to itself. 1, 2 coming back to from V1 to itself through V3. 1, 2 coming back to V1 from V1 to itself through V5. Okay, so I have 2 walks from V1 to V1, and there are 3 of them. Okay. Okay. do I have, so let's write here 3. V1 to V1. Okay. Do I have an edge from V1 to V5? Yes. Okay. Because if I do the row by column multiplication, I'll have this. Okay. 3 times this one. Okay. This means there is an edge V1, V5. And so 1, 2, 3, 1, 2, 3, and 1, 2, 3 gives me 3 walks going through V1. Then what do I have? One, 2 walk from V1 to V2. And here it is. 1, 2. Okay. And so I have plus 2, which means from V1 to V2, but times 0, no edge, V2, V5, okay? Plus, let's see, from V1 to V3. From V1 to V3, I have a 2 walk. Well, just 1 2 walk is written here, which is this one, okay? So, plus 1, which is from V1 to V3. But times this 0 here, because again we have no edge between V3 and V5. Plus, let me go here, plus, after that what do I have? A 3 here, from V1 to V4, I have 3 2 walks, and here they are, 1, 2, 1, 2, and 1, 2, okay? So 3, which are walks from V1 to V4, and it's multiplied by this one, which means there is an edge between V4 and V5, times 1, which is there is an edge V4, V5. And finally, I have 0, 2 walks from V1 to V5, okay? And, okay, so 0 and no walks, no 2 walks. V1 to V5 times 0, no edge, V5, V5. Okay, so this is exactly this product, row by column, which gives us in a third power at the position 1, 5, gives us what? This number here, 3 times 1 plus 2 times 0 plus 1 times 0 plus 3 times 1 plus 0 times 0, which is 3 plus 3, which gives us a 6 here. Okay, and this means there are 6 3 walks from V1 to V5. How did we count them? By saying how many 2 walks from V1 to itself? 3. Do we have a final edge from V1 to V5 in order to make out of these 3 2 walks to make 3 walks? Sure thing. 1, 2, 3. 1, 2, 3, and 1, 2, 3. Okay. Then we have two walks from V1 to V2, okay? But they are not the starting part of a 3 walk from V1 to V5. Why? Because we do not have any final edge from V2 to V5. And so let it have two walks from V1 to V2, but we cannot complete with the final edge. And so it's times 0. From sorry? Oh, yeah, sure. Thank you very much. Yes, it is this one. Thanks a lot. So I correct, and thank you very much. We have 1 to walk, and it is very evident from V1 to V2, the only 2 walk is this. But we cannot complete it to a 3 walk from V1 to V5. Why? Because we have here a 2 walk, but no third edge from V2 to V5. And this is given by this 0 here in the adjacency matrix, okay? Then we have 1 to walk from V1 to V3. But again, we do not have a final third edge from V3 to V5 in order to make out of it a 3 walk. So 1, yeah, but times 0. And then we have 3 2 walks from V1 to V4. And here, each of these 2 walks can be completed by a third edge going from V4 to V5. And this edge is represented by this one here in the adjacency matrix, okay? And finally, we do not have 2 walks from V1 to V5, and we also do not have edges from V5 to itself, okay? And so here, by summing these walks, which can be, the numbers of these 2 walks, which can be completed by the presence of an edge to a 3 walk, we have that this sum gives us the number of 3 walks from V1 to V5. But this is nothing but the natural inner product of this 5 tuple with this 5 tuple, meaning exactly this element here in the row by column product of A squared times A. Okay? It's not important that, to check, but you can check that this is actually the matrix of the 2 walks. We assume it in our proof, we have assumed it as the inductive hypothesis. And out of this argument, we deduce that if this is the matrix representing the numbers of 2 walks, this necessarily represents the matrix of the numbers of 3 walks. Okay, and since we have from the beginning our inductive premise proved, we are sure that we get the general result. And so A to the 4th will be made of the numbers of 4 walks. A to the 1000s will have the numbers of the 1000 walks from one vertex to another. Don't forget this thing, because it was suitably modified. I'll show you that it is important for Google rank. Okay, I'll give you later. Now we have to focus on the course, on the book, but later I'll give you some marginal talks on something which is not part of the exam, part of the program. And one thing will be how come Google works so well in finding what we are looking for. One reason is in this type of construction, suitably modified with probabilities and with directed graphs. Later, okay? Okay, now next exercise, the one I did not solve so far, and I'll solve it now. So, I have D1, D2, Dn, okay, where for each I, the I is non-negative integer, and I also know that sum for I from 1 to n of these numbers di is even. How do I construct my graph? Has anybody found a solution? Okay, no. So I'll do it myself. Did you? Okay, so I'll do it myself. Okay? I take n vertices v1, vn. For each I, if the I is even, I put di divided by 2 loops on vi. If di is odd, I put di minus, no, not here, di minus 1 divided by 2 loops on vi. Finally, I connect pairwise by an edge, vertices, VR, VS, for which DR, DS are odd. Okay, and this is quite a general rule. I can do this final connection just following the row. And so let's take, for instance, oh, here I could. Can you tell me those sequences 7? Oh.
was 7, 6.
Without the face mask, please.
7, 6, 5, 4, 3, 3, 2.
Okay, so V1, V2, V3, V4, V5, V6, V7. 7 is odd, so 7 minus 1 is 3, so I put here 1, 2, 3 loops. 6 is even, so I divide by 2, 1, 2, 3 loops. 5 is odd, so 5 minus 1 is 4, divided by 2, I put here 1, 2 loops. 4 is even, so I divide by 2, 1, 2 loops. 3 is odd, so 3 minus 1, 2 divided by 2, just 1 loop. Same thing for this 6. And V7 is 2, which is even, so just 1 loop. And then where am I left with an empty valence? Here, V1, 7, and the next one is V3, so here. And then V4 is all right like this, and then here and here. Here it is. But it's not just a solution for this particular seventh code. My recipe is valid for any such sequence. Okay? You want to tell me how ugly it is? I absolutely don't care. Have I solved the problem? Yes. Was there a requirement of beauty? No. So my solution is valid. An engineer must find the correct constraints. This is very important. Exercises like this give you constraints, okay? And you must solve them within those constraints. This is a big difference between mathematicians and engineers. A mathematician only wakes up when all constraints are set, when all hypotheses have been written down. And then he starts his machinery, okay, like in our exercises. The engineer must look for, build his or her constraints, modify his or her constraints, okay? Adapt to the existing constraints, maybe build some, even if this may look silly, sometimes you have to put some constraints which are not there from scratch, okay? And then with those constraints, you work, okay? You can then adapt a mathematical model. Okay, this is a very big difference between engineers and mathematicians. Okay, so I solved this. And let's go back here. There was another problem left, but this is rather easy. Well, okay, let's do it just by words. We have small delta greater than or equal to 2. Let's show that it contains a cycle. That's very easy to tell just by words. Small delta greater than or equal to 2. Okay, pick up any vertex. Of course, it is not isolated because it has at least 2 edges. Okay, go out of this vertex by an edge. You land in a second vertex, okay? But in this second vertex, you have an escape road. Why? Because also for this vertex, the degree is at least 2. So you have already used one of its edges, but you have at least one to get out of this vertex. and you land in V3. How, one could say, who knows whether it is V3? It might be V1. Oh, if it is V1, we are absolutely happy because we have already closed our cycle. No, it is a V3 which is different from V1 and V2. Yes, but also for V3 we have entered through an edge. We have at least one edge to get out of V3, and so on and so forth. Eventually, sooner or later, we must go back to what? Necessarily to V1? No, not necessarily, but to one of the already seen vertices. Why? Because our graph is finite. All our graphs are finite. There is a big branch of graph theory dealing with infinite graphs. This is not the goal of this course and of this book. Our graph is finite, so eventually you land back into an already visited vertex. Then you close your cycle. You forget the initial part if you had an initial part, and you close your cycle in this way. Okay, maybe you land in V3, you have V1, V2, V3, V4, V5, V6, and again V3, okay, forget about V1 and V2, and you close the cycle from V3 to V3, okay? Good. No more problems now, and now let's face this problem, this class of problems, which is very interesting, which is this. We have, as I said, a weighted graph, meaning that on each edge we have non-negative real number, which we call a weight, but in general it can be a cost, a length, a time to travel, whatever you want. Okay, but the goal is that you want to reach from a particular vertex which you decide, which nature decides, that your customer decides, a particular vertex to every other vertex. You want to have a path connecting that particular vertex to all other, in which every path you build is of minimal sum of the weights from that particular vertex, which we call here U0, to that other vertex in the graph, okay? This maybe looks silly if you have that you want, as in the case of the navigator, you want to connect two particular points, okay? You might have that you want to reach V0 starting from U0. Still, this method, in its basic version, looks for all minimal paths from U0 to any other vertex. In reality, it's not like this. In reality, there are many constraints. You remember what I said just before? Many constraints that you can put on this algorithm in order to have less and less and less computations. But the principle is always find all minimal paths to all vertices. Now, not in all graphs, because the graph of Italian roads is too big, of course, and it would be silly if I want to go from here to Modena, 37 kilometers away, to also find a minimal path from here to Naples, okay? In principle, Dijkstra's algorithm does exactly this, finds a minimal path from, say, Bologna to all other towns, okay? But in reality, you have, there are very, very nice ideas to put constraints and limit the number of computations, okay? But now, so now let's face this problem. We have a particular vertex U0, and we want to have a minimal path to any other vertex in the graph. Is the problem clear? Okay. So now here there is much which is written, and since this will be anyway surely one of the questions in your midterm, I show you how to deal with this. Okay, so we start from our U0 and we put there the distance from U0 to itself, which is 0. Okay, and now you start by looking at the neighbors of U0. Okay, and you have here, these are the weights which are already there. So we have a 1 here, an 8 here, a 4 here, a 2 here, a 7 here. Okay, so what is the nearest to U0? In this case, it is this vertex having, let me call it distance 1, okay? Assume that all these are lengths of rows, okay? So this is at distance 1. So we take in this edge, and we also put here the distance that we have discovered. It is necessarily the least possible from this vertex to this vertex. There is no other possibility for having a smaller total. Okay, you might have in other cases. Let me look here. Yes, look here. If I want to go from here to here, even if I have just one edge, it's not the shortest path from here to here, because I have a shorter path through this edge. It doesn't look like that, but you must not rely on your eyes, but on your numbers. 4 plus 2 is less than 8, okay? And so the shortest path from U0 to this is not the direct one, but this one. So if we want a shortest path starting in U0 of length 1, we just have to take the minimum, the only or one of the edges with minimum weight. And in this case, it is this. So we take in this edge, take in this vertex, and put on this vertex the distance that we have from U0, which is 1. And here it is what we have done, okay? So now we have already taken in, of course, U0 and also this one. Now, remember that it's always U0, the protagonist, the main character of our movie, okay? And so we are interested in minimizing things from U0. So now let's look. 0 plus 2 is 2. 0 plus 7 is 7. 0 plus 4 is 4. 0 plus 8 is 8. But we also have 1 plus 2, 1 plus 7, 1 plus 3. Okay? But these are all greater than this very simple 2. Okay? So if I'm looking for a vertex which is at a minimum distance from U0, except this one which has already been taken in, we have this one. Okay, so we take in this edge, this vertex, and put here the distance, which will be 2. Okay. All right. So now let's see. From U0, we have 7, we have 4, we have 8, but also we have 1 plus 7, 1 plus 3, okay? And from 2 we have 2 plus 1, 2 plus 5, okay? So this time we do the closest to U0, apart from the 2 we have already taken in, it's not one directly joined to U0. Why? Because here we have 4, which is the least one of the remaining 3 from U0, but we have 2 plus 1, which is less than 4. Okay, so 2 plus 1 is 3, so we take in this edge, this vertex, and we put here 3 for saying that 3 is my distance from U0. Okay? All right, so now, what do we have? We have now 1, 2, 3. Is there anything else with the 3? It should be done by something starting from U0, nothing has distance directly 3. So 1 plus something could be 3, but this is 1 plus 3, this is 1 plus 7, this is 2 plus 5. Okay, so nothing more at distance 3. Okay, let's see whether we can get distance 4. But yes, we can get distance 4. This one is an edge of weight and length 4. Okay, so we only now can we take in this edge and this vertex and put the 4 here for saying, okay, this vertex is at distance 4. Okay? And we go on like this. Now, do we have anything else at distance 4? Let's see. 1 plus, no, already done. From here, we have 1 plus 7. Okay, no use. From here, 2 plus 5, no use. From here, we have 3 plus 3, which might be interesting. Okay, or 3 plus 8. And from here we have 6 plus 2. Oh yes, we had still 7 here and 8 here. Now we have 4 plus 2 and 4 plus 3, 4 plus 6. Okay, so at distance 5 we do not find anything. Okay, but we have something at distance 6. We have this 4 plus 2, and we also have this 3 plus 3. Okay, now it is unimportant which you choose first, since they both are at the same distance, which is 6. Okay, so the authors in this case choose to take in this edge and this vertex, but they could very well now take in this edge and this vertex, because they both give us distance 6. So here we have distance 6. Look, it says that it's better to go this long way from U0 to this vertex instead of going directly. Okay? And after that, we also have, of course, this could have been before, it is after the same thing. And of course, we have this last vertex, but of course, we now take this last vertex, but through which edge? Oh, okay, minimizing the total length. And so, how can we reach this? By 6 plus 4, which is 10, or 4 plus 6, which is 10, or 6 plus 4, which is 10, or 3 plus 6, which is 9, which is less. Okay, and so finally, we take this edge and we have distance 9, okay? So you see, this is what is called Dijkstra's algorithm, and finds minimal paths from a particular vertex to all other vertices. Of course, if you have a long path like this, we have necessarily that this is a minimal path from U0 to this vertex. For getting to the intermediate vertices, you still have parts of this same path, okay? Good. And what we get is something which has necessarily no cycles, okay? It is necessarily connected. Do you remember what it means to be connected for a graph? It means from each vertex to each vertex, there is at least one path connecting them. Okay, this thickened subgraph given by the minimal paths from U0 to all other vertices, this minimal this subgraph is necessarily connected because every vertex is connected to U0, and so possibly going through U0, you can reach each vertex starting from each vertex. Do you remember? It is my trip to Singapore, okay? I had to go to Paris, okay? You think, oh, look, if I want to go from here to here, I could very well go through this edge, okay? But if the U0 airline has very good fares, it is better for you, instead of going directly through this, to go to this hub and then to this, okay? Why? Because for U0, the U0 airline, they do not want to put many aircrafts on service, okay? They can reach every vertex just by one path, and so they do, okay? It's not true. Actually, in the true airways, you have cycles, okay? But in principle, you could have no cycles if you want to be extremely greedy and you want to spend really the least possible, which connects you in Paris to every other town, every other airport in Europe, okay? You can do it without building cycles. If you build cycles, evidently you have two ways to reach the same place, and this means that one of the two is superfluous, could be avoided, and you still reach from Paris that particular town, okay? Remember this in the next chapter, which is trees. Oh, sorry. Yeah, thank you. Thank you for answering.
Myself.
Answering yourself, yeah. Okay. But it's good for everybody. It's very good if you use the chat for discussing, suggesting among you. Okay. All right. So trees. This is one of the long chapters, meaning that when I give you my subjects for the exam, one of the two titles I give you can be trees, or can be graphs and subgraphs, or can be vertex colorings, or can be directed graphs or planar graphs. These are the long chapters, okay? And I'll give you, I repeat, I'll give you two titles to choose between, and each of the two titles is either the title of a long chapter like this and like the preceding one, or the sum of two titles of short chapters as connectivity, matchings, Euler tools and Hamilton cycles, okay? All right. Now, trees. Trees are important by themselves. There are some classes of graphs which are important because you find them quite often in applications. One is bipartite graphs. Okay, why? Because you might have that what you are modeling with the graph actually has two types of vertices, okay, and the edges actually put a relation just between vertices of one of the two types, the vertices of the other type, and never between each other, okay? And another type of graphs which is met quite often in applications is this, trees. What is a tree? Please always start by definitions. A tree is an acyclic graph which is connected, a connected acyclic graph. Connected we already know. Acyclic means there is no cycle in this graph. Okay? So please do start from the definition. Otherwise, we are talking about something, but we do not know what we are talking about. First of all, know what you're talking about. First of all, you write down an equality, and inequality, there are quite a lot in the course. Do not write it if you do not know the meaning of each of the symbols. Immediate rejection. If you write from your very good memory, you write down all formulas, and I ask you, what is this symbol? And you do not know, reject it immediately. I prefer that you say, I don't remember the formula. Much, much, much better than writing a formula of which you do not know the meaning. In the first case, you are a bit not very good engineer, but a reliable one. In the second case, you are a non-reliable engineer. Okay. Two theorems. The first, okay, is also important, but I like very much the second one. First theorem about trees. In a tree, any two vertices are connected by a unique path. That there is at least one path is given by the definition itself. A tree is connected by definition, okay? But existing between any two vertices, guaranteed by the connectedness, is unique in trees. Let's see the proof. The proof is by contradiction. We take a tree, but assume that there are two distinct UV paths, P1 and P2, meaning a path P1 connecting U to V, a path P2 connecting U to V, and they are different. What does it mean to be different? That they differ by at least one edge. They might have some common edges and vertices, but at least one edge is different between P1 and P2, okay? So there is an edge, call it E, and let it be between vertices X and Y, which is an edge in P1, but does not belong to P2. Now take the graph given by the union of vertices and edges of P1 and P2, okay? And what? Take away edge E. This is connected. Why? Because even if you have broken path P1, still you have path P2 through which you can go from each vertex to each other vertex of the graph. So it is connected, okay? So there is an XY path P, okay? XY path meaning what? Remember, X and Y are the two ends of this edge we have taken away. But even if I take away this edge E, if I take all vertices and edges of P1 and P2 apart from E, we have it that it is connected, so it means what? That from each vertex to each other vertex of this graph, there is at least one path. And so in particular, from X to Y, there is this path. But then, if I put back so let call this path a surely existing path P, but if I put back E to this path, which connects X to Y, of course not passing through E because E is not there, if I put back E, then a cycle appears. But this cycle was already present in G, but then this means that G was actually not a tree. Why? Because a tree, by definition, is acyclic, without cycles. Okay? Can we also reverse this? Meaning, if I have a connected graph for which there is a unique path from each vertex to each other vertex, can I be sure that it is a tree? Yes, for graphs without loops. Okay? If we have a graph without loops, for which we know already that it is without loops, and for which from each vertex to any other vertex there is a unique path, then it is possible to prove that it is actually a tree. And this is an exercise, but not in our list of exercises. Here is this, just to show you that just by brute force we can also think of drawing, putting down all trees with a given number of vertices, and you can see also this is a nice zoo of trees, because you can see how a tree can be like this, okay? And intermediate things up to this, which is a path, okay? This will be important in one of the exercises, okay? And there are things which you can see already here. One is this corollary to 2. Every non-trivial tree has at least 2 vertices of degree 1, okay? And you will have an exercise about this number 2 of vertices of degree 1. There is a a funny thing about this drawing here, okay? There was some years ago a movie with Matt Damon called Will Hunting. A young person cleaning the corridors and classrooms of a big university, okay? And the big professor discovers that this cleaning man is actually a mathematical genius. And how does it start to discover it? Because he gives a problem, and that is an American university, so they have money, and so they have blackboards all around the building, so they have blackboards on the corridors, and on one of these corridors the professor had put a certain question for the students, and the professor, by going through the corridor, discovers that it has been solved. And what is on the blackboard is exactly this drawing. Okay, they evidently they wanted to have something rather nice to show on a blackboard, and they had this book, and they that's a nice drawing. And so this is the first problem that Matt Damon solves in that movie. Okay, back to this, which is the theorem I like more. I very often ask this theorem and the proof of this theorem, which is very nice, okay, by induction. Okay, if G is a tree, then epsilon equals ni minus 1. The number of edges equals the number of vertices minus 1, okay? We do it by induction on the number of vertices ni, okay? I'll have to tell you a little variation on what I said about proof by induction, but let's see. The inductive premise, ni equal to 1, so we have just one vertex. Then it has to be a cyclic, this graph with one vertex. What with one vertex? Either you have no edges or you have loops. And if you have even just one loop, you do have a cycle. So with one vertex, you must have no edges for it to be a tree. It is a tree. Is it connected trivially? Is it acyclic? Yes. Okay. So if you have a tree with just one vertex, it must have no edges, and so epsilon is 0, which is exactly ni, which is 1 minus 1. So inductive premise, as almost always, is very easy. Now, let's assume, generally, well, in my version, which is the most used, I said, assume that the thing works for h minus 1 and show it for h. Here we assume that our statement, this is valid for, not just for ni minus 1, but for smaller than ni with trees with less than ni vertices, not just ni minus 1, but also ni minus 2, minus 3, and so on. For all trees on fewer than ni vertices. We assume that it is true. Inductive hypothesis. The theorem is true for all trees on fewer than ni vertices. Okay, now let G be a tree on ni vertices with ni at least 2. Okay, since 1 is already settled, let's start with 2. Now, pick up any edge of the tree. Okay? Take it away. This edge, let's call it UV, meaning U and V are the two ends of this edge. Take it away. There is no UV path. Why? Because the edge UV in G is the only path between U and V. We have proved it before. Since there is an edge between U and V in G, which is a tree, then this is the only possible path between U and V. If you take this away, then you're left with no paths from U and to V, which means that G minus this edge is disconnected, is not connected. Why? Because there is a pair of vertices which are not connected by a path. So, okay, what you have is that you're left with more than one component. In particular, it's two components, okay? It's possible to see that it is two components, one containing U and one containing V, okay? But in each of these components, the two pieces, the two connected pieces you are left with when you take away edge UV. Do they now contain cycles? No. Why? Because if these components contained cycles, these would be cycles also belonging to G. But G is a tree, so it's not possible. So each one of the two components is connected and is acyclic. So they are trees. So the two components, call them G1 and G2, or G to which you have taken away edge UV, are trees. So for each, and of course they have less than vertices, okay? Because one does not have V and the other does not have U. So they surely have at most ni minus one vertices. And so for them, our relation works. So let's take our induction hypothesis, says that for G1, epsilon of G1 is ni of G1 minus 1. For G2, epsilon of G2 is ni of G2 minus 1. Now, what about the total number epsilon of G? What are the edges of G? The edges of G1, the edges together with the edges of G2, together with one edge we had taken away, the edge UV. So we have epsilon of G1 of G equals epsilon of G1 plus epsilon of G2 plus 1, where this one is exactly due to this edge here. But now we can apply the inductive hypothesis. Epsilon of G1 is ni of G1 minus 1. Let me write it down. So epsilon of G equals epsilon of G1 plus epsilon of G2 plus 1. Epsilon of G1 is ni of G1 minus 1. This is ni of G2 minus 1. And then we have plus 1. But then I can do, say, this with this, and what I'm left with is ni of G1 plus ni of G2 minus 1. But mind, what about the number of vertices of G? When we take away edge UV, we do not take away any vertex. So all vertices of G are either in G1 or in G2. And so this is actually ni of G minus 1. And so we have proved the statement. This is a very simple but very meaningful use of the induction technique. And so I absolutely want you to understand and to be able to reproduce it in an exam. Okay? 5:15, let's say. Okay, okay, let's do it 17:30, 5:30 Italian time. We start back now, a break. And then we end anyway at 6:45 Italian time.
For myself.
Pardon me?
2 questions for myself.
Oh, sure. And I go on recording then. Tell me.
Bring your notes.
Yeah.
For the exercise 1.155 from the beginning of this page, I didn't understand this part. Next, yeah, exactly.
This
765. One. The loops, yeah, I don't understand it. But I got disconnected. Would you please explain again?
Sure. Wait a minute. Here. Okay. So, what was my goal? You give me any sequence of finite sequence of non-negative integer with the only constraint that the sum of these numbers is an even number. Okay. And out of this, I must give you again, I must build an algorithm, a procedure, so that if you give to that procedure such a finite sequence, then the procedure must output what? A graph for which these are the degrees of the vertices, okay? First thing, well understanding the problem. Is the problem clear?
Yes, sir.
Okay, now my solution. My solution is, okay, n numbers, of course I take n vertices, all right? And now I must put there the edges so that for V1 the degree is D1, for V2 the degree is D2, and so on and so forth. All right? Okay? Okay, so what is the procedure? This could become a computer program. Do you see what I mean? Okay, so I take one by one these numbers. If the number I'm taking is even, okay, D1 is even, then on V1 I put half of D1 loops. Why? Because each loop counts for 2 in the degree. Don't forget that. Okay? If it is odd, if the number is odd, I cannot put that number divided by 2 is not an integer, but I can take 1 away. I'm left with an even number, di minus 1 is even, and that I can divide by 2. And that is the number of loops I put on that particular vertex. Okay. Now I'm left with some vertices which have saturated their degree, and some which, for which a 1 is missing, one edge is missing, okay? But remember, the sum is even, and so there must be an even number of odd numbers. Sorry for the seeming pun, okay? There is an even number, di, which is odd, okay? And so I can connect them pairwise. I connect the first odd with the next odd, and then the next odd with the next odd, and so on and so forth. This is the general rule I have use as a procedure. Sorry, this is equal. Yeah, so I can take it this way. Okay, let's look here. This particular sequence, which was taken by from the book, 7, 6, 5, 4, 3, 3, 2. The sum is even, and so necessarily the number of odd numbers must be even. So I can take them by pairs, since it's an even number of odd numbers. So V1, I take 7, 7 is not divisible by 2. So I take 1 out of 7, which is 6, divide by 2, and so I put 3 loops here. 6 is even, no problem. I divided by 2, 3 loops. 5 is odd, 5 minus 1 is even. Divided by 2 is 2, 2 loops. 4, 2 loops. 3, 3 minus 1, 1 loop. 3, 3 minus 1, 1 loop. 2, I just divide by 2, 1 loop. But if I do not put this, I'm left here with degree 6 and here with degree 4. And that's why I put an edge between this and this. And so I reach 7 on one side and 5 on the other side. Same thing here. There must be pairs, as I said, of odd degrees. And so I am left with the 2 here and 2 here. I put an edge which makes 3 and 3. And so on and so forth. Give me any sequence with the constraints we have said, and I'll construct a graph with exactly that sequence of degrees. Is that clear?
Oh, yes, sir, I got it. Thank you so much.
You're welcome. So now I interrupt the recording.
Please excuse me. The next proof we had for 172, show that theta origin in G contains a cycle. Exercise 172.
Okay.
write down one line of mathematical proof for it instead of an explanation one, a wordy one?
Okay.
Sorry.
Oh, okay. Small delta is greater than or equal to 2. Pick up any vertex, call it V1. V1. Use one of the edges incident on V1 to go to another vertex. Call it V2. Since small delta is greater than or equal to 2, then degree of V2 is greater than or equal to 2, so there is at least one edge incident on V2 that we have not yet used. Okay?
Perfect. Thank you so much.
No. Let me, there is still something to say.
Okay.
Going on like this, I always have at least one edge to exit a vertex which we have entered. But the graph is finite, so eventually we meet a vertex that we had already used. This closes a cycle. Look, it might be like this, that I start in V1, go to V2, go to, and here I have several edges, okay? And then I go to a certain V3, and then, and here again, and I can get out to a certain V4 and to a V5. And maybe the repeated one, let me put another one, V6, and maybe the repeated one is not V1, but V3. Okay, but then V3, V4, V5, V6, V3 is the cycle we wanted. Okay? Okay.
That's great.
Okay.
Yeah, I got it. Thank you so much, sir.
You're
Thank you.
welcome. So now I interrupt.